Hi, this is Mr. Kim, and today we're going to talk about two-dimensional conservation of momentum, which is lesson 3 of Unit A. Again, this is Physics 30 curriculum in Alberta, so have that in your mind just in case if you're from other places. Alright, so let's get this started. As you may see, the picture is not that different compared to previous video. I have a collision going on the right side of the screen. So, for example, as you may see that the car in the upper picture is actually going towards you. If you're in the perspective or going out of the page, you can think it in that way. It is coming towards you. However, look at the impact that is happening on the right side. As you may notice, the car that has headlights on, it is undergoing a collision that went sideways. So you may notice that because of this impact or momentum, you may see that the bus or car in this case is, instead of going towards the direction that it was going, it is actually going away from it. Now it's two-dimensional situation where it's not only one direction situation now, we're going to look at the other dimension. If you look at the picture on the left side too, I have stationary dynamite or whatever explosive material you can think of. It is undergoing some kind of explosion, and look what happened. It went diagonally. First of all, in Physics 20 and Physics 30, these situations we call it two-dimension because mathematically speaking, two-dimension means we have positive and negative y-axis that goes up or down. Generally, if it's like a navigator method, it is north and south. And when it comes to x-axis, positive and negative again. And these two defined two-dimensional images. If you watch any of animation, like Family Guy, Simpson, it's all two-dimensional in there. There are some three-dimensional component, but we're going to get that probably in university if you choose to go to physics field and you'd use calculus. Now, let's not take any side way. If you want to do some hands-on activity that involve precise speed, mass arrangement, and momentum effect, when it comes to two-dimensional situation, I highly recommend you go to VET Colorado website and put Collision Lab. It is the same app that we used before for one-dimensional conservation of momentum situation. Let's do a little bit of example. Let's talk about car. If you have a car collision, you generally stick together. And think about this example as car collision, or you can think of two of the clay balls traveling in different direction and they stick together. What's going to happen afterward? So let's look at this situation. I have object number 1, the green one on the left side. And I have object number 2, the red one. As you may notice, they're traveling in different dimension. One involved x component. So as you may notice, I put P1. Some people who like mathematical approach, you can actually put P1x just in order to show you that this is a horizontal component. When you look at the other one, P2, it's P2y. Because it is going up-down situation. What's gonna happen when these two collide? Well, whether they stick together or not, you may notice that from our Physics 20 concept, you need to think about our tip to tail diagram in order to understand the resultant vector. Because I know that the object number 1 will go towards east. Let's put east or right. And I have object number 2 that is basically heading north. So if I think about my vector, which is our resultant value, the one that I'm drawing in dot right now, is basically representing our P12 situation. It is combination of both first object and second object situation. And we have our angle from our initial point. If you reverse this situation, so for example, imagine you put P2 first. It really doesn't matter. You need to touch the tail and head together in this way, and that will make 90 degrees, so as what you see on the left side. And if you connect those as a hypotenuse, and yes, as long as you see that the resultant vector, in this case, it's hypotenuse of those tip-to-tail diagram situation, you're on the right track. The only difference is your angle, your navigator method angle, should be written differently. So, oops. Here's basically what happened. They're gonna stick together and they're gonna travel diagonally. As long as you include an angle, either start from the bottom or up to the right, any of those answers is acceptable. Again, value of P12 will not gonna change, it's just the angle that will change. And these P1 and P2, using Pythagorean theorem, we can find the quantity of our net vector when it comes to SOHCAHTOA. We can use it for finding our angle, navigation method. That's a fancy way of saying, if you recall, north of east, east of north, those kind of thing. And make sure that in this situation, we're still talking about isolated system where there's no external force that interfere the situation, so my initial and final value should equal each other. So let's get this started in terms of actual class example. I'm gonna do one classroom example and finish this video, and I'm gonna show you another one. Let's read the question. A 1,200 kilogram car moving west at 14.2 meter per second. It collides with a 1,900 kilogram truck moving north at 16.0 meter per second. If they stick together, determine their final velocity, both magnitude and direction. So let's get this started by doing diagram. Generally, the first step that I do is I draw tip to tail diagram. I'm gonna call this 1,200 kilogram car as number 1. I'm gonna call 1,900 kilogram truck number 2. Generally, I use ball or box in order to show you the situation. Now, before we draw tip to tail, let's visualize this situation. So I have basically number 1 car moving towards west. And I have number 2 car that is moving towards north. And basically the reason I draw this is because so that I can pay attention to these two's vector. So I can say in the way that, well, again, the order doesn't matter. I have P1. If you want to put X, that's also good. And I have my P2 that is directly going towards y. And when you see this x and y connection, they always make 90 degrees. Here's my resultant vector. That's what the question is asking. Well, indirectly asking. Eventually the question asks you to find final velocity. However, it is important to find out momentum first. So this is my first step. Second step, generally I list what's given. What I mean by that is M1, 1,200 kilogram. M2, 1,900 kilogram. V1, initially, I have 14.2 meter per second. Now, this part we need to be careful. As you may notice that diagonally it's going west and north combined. So probably what I'm going to do, I'm going to decide west and north as positive so that everything will be positive. If you want to have west as negative, I'm not going to stop you. And the other clues, which is my 16.0 meter per second. Now, have that in your mind that when it comes to our resultant vector, we need to find momentum's values, both x component and y component, and we need to use our Pythagorean theorem after that. So my second step, third step play a huge role in here. I can put M1, V1, M2, V2, and I can punch these numbers in and find out the answer. Now, we do know both of the momentum. The one that involves x component is this. One that represents y component is this. Now we can apply this to our good old Pythagorean theorem, except we're isolating for c. There you go. Which is hypotenuse. So, our last step, which is our third, find the resultant vector. And I believe significant digit was 3 significant digits, so I can say funny thing is, are we completely done? No. Unfortunately, we need to find the angle, which is easy. We just need to use our SOHCAHTOA. Don't forget that we're using second function of tangent in here, and the reason I'm using tangent is because they're a whole number, so that's why. And I can just put SOHCAHTOA opposite over adjacent. In this case, opposite is our good old y component, so you get roughly 60.7 degrees. And always remember, when it comes to navigator method, the second letter represents where you start having that angle, which is west. First letter represents where it goes toward. So 60.7 degrees north of west. You may choose to use different angle. If you do 90 minus 60.7, then it will be turning into west of north. This is our first video for lesson 3. Thank you.